Hello everyone, welcome to the video. Today we are going to solve the problem minimum number of jumps. In this problem, we are given an array of integers and every element in this array represents the length of the maximum jump that we can make. For example, the number 3 here indicates that we can jump till 5, till 8 and even till 9, but not beyond that. So this is given to us and we have to return the minimum number of jumps that are needed to reach the end of the array. And if any of the element is 0, that means we can't move through that element. We can't jump any position from that element. In case we can't reach the array, we have to return -1. In the previous video, we solved this problem using top-down dynamic programming approach. In this video, we will be solving this problem using bottom-up dynamic programming approach. Later, we will also see a further optimal approach to solve this problem, which has a better time complexity than the dynamic programming approach. So we will solve this problem today. We will go through the thinking process, write the algorithm, and then also see a working code for it. But before we start, if you are new to this channel, please don't forget to subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given that there are n integers. They are present in an array. And every element of that array represents the maximum length of the jump that we can make from this position. And what we have to return is the minimum number of jumps that we need to reach the end of the array. It is also given that if the element is 0, then we can't jump from here. And if it is not possible to reach the end of the array, we have to return -1. If we consider this array as an example, then here to reach the last element, we will need to make at least 3 jumps. For example, first jump till 3, second jump till 9, and then third jump till last element of the array. So if we consider our solution as a black box, we are getting an array as an input and we have to return the minimum number of jumps. So what will our function signature look like? Our function signature will look something like this. Before moving to the bottom-up approach, let us first see how did we derive the recursive relation while solving using top-down approach. So this was our array. Our aim was to reach the last index from first index in minimum number of jumps. So we made a few observations. We thought that to reach any index I, which may be the last index or may be any other index, to reach any index I, we will have to jump. We will have to make a direct jump from some index j, which is prior to I. So this was our first observation. Then a jump from j to I is possible only if aj is greater than or equal to I minus j. This was our second observation. And we can reach I from j only if j is a valid candidate to jump from. That means j itself is reachable. Because if j itself is not reachable, then there is no possibility to reach to I via j. Therefore, minimum number of jumps to reach j should not be equal to -1. Because with -1, we denote the position which is not reachable. And now, satisfying all these 3 conditions, there could be multiple j. But since we are interested in minimum number of jumps, we will have to take the minimum of such value. Therefore, our recursive relation was looking something like this. Minimum number of jumps needed to reach the index I is equal to minimum number of jumps needed to reach the index j plus 1 and minimum of all these. Which j's? All j's such that they are less than I. Aj is greater than or equal to I minus j. That means it is possible to jump from j to I. And minimum number of jumps to reach j is not equal to -1. This was our recursive relation that we derived. Then we converted this recursive relation into algorithm. We also added our base conditions so that this recursive algorithm is complete. Then we introduced a map to take care of the overlapping problems. so that for the same input we don't have to calculate again and again. So this was our top-down dynamic programming algorithm, and now the next step is to think of the bottom-up dynamic programming algorithm. But why bottom-up? What is the problem with top-down? The problem with top-down approach is the same as the problem with recursion. In recursion, the same method keeps on calling itself till the base condition is reached. Therefore, there are a lot of method calls. Now, every method call occupies some space in the memory. But with recursion, since there are multiple method calls, a lot of memory gets occupied. So it would be great if we could solve this problem in similar time and space complexity, but without recursion, so as to avoid occupying that extra space. And that is why we need to think of the bottom-up approach. So what is bottom-up approach? In the top-down approach, we start from larger input and progress towards smaller input. What does that mean? That means that we start with the input that is given to us in the question. We call our recursive method first with that input, and then as the recursion progresses, the input goes smaller and smaller till we reach the base condition where we get our answer. So this is how the top-down approach progresses. In the bottom-up approach, we progress in the reverse direction. We first calculate the answers for smaller problems or our base conditions. Then we use them to calculate the answer for further larger problems, and gradually progressing in this manner, we ultimately reach the answer for the input that is given to us in the question. For example, here input is the index till which we can reach. And what does input getting smaller mean? Input getting smaller means the index that we have to now reach is smaller than the original problem's index. We will still use the recursive relation. We will still use the answers of smaller problems to derive the answer for larger problems, but we will do this in the reverse direction. This means we still need to store this information that for an index I, what is the minimum number of jumps required to reach this index. We will still need to store this information. So what can be the best data structure to store this information, and also we can gradually progress in that data structure from smaller index till larger index. That data structure can be a one-dimensional array. So this one-dimensional array can store answers for every index. So every value at any position will denote what is the minimum number of jumps required to reach this index in our given array. So what will be our final answer? Our final answer will be the value at this position, because this will denote the minimum number of jumps required to reach the last index of the given array. Okay, so now we know that this will be our final answer. That means if we can fill this array, our job is done. But how do we fill this array? Let's see how do we fill the value at any position in this array. Let's say we want to fill the value at this position. That means we want to fill the value of minimum number of jumps required to reach the index I. Now, as per the recursive relation, what all information do we need? We need this information, minimum number of jumps to reach j. That means we will have to fill all of these values. We also need this information. What is the value of aj? We obviously have this information since we have the original array. And we again need this information that minimum number of jumps to reach j should not be equal to -1. We will obviously have this information if we have filled this part of the array. So we know that we have to fill this array from left to right, and using this recursive relation, we can fill the value at this index. So now we know that our final answer will be this. We also know how will we fill this array. We also know how will we fill value at any position and in which direction should we fill this array. But how do we even start? From where we will start? Let us come to our base condition. What is our base condition? Our base condition is when index is equal to 0. So what is the number of minimum jumps that we need to make to reach this index? The problem says that we are at the starting index in the beginning. That means to reach this index, we don't have to make any jumps. Therefore, the minimum number of jumps to reach this index will be 0. So now we know how to start filling this array, how to fill the value at any position I using the values of previous positions j, and we know what will be our final answer. So we have everything that we need to convert our thoughts into algorithm. So let's try doing that. Clearly, we need a one-dimensional array of size n. We need to fill its first element with value 0 as per the base condition. Then our aim is to fill whole of this array. So we will have to iterate. And in every iteration, we will be focusing at a particular index I, and we will try to fill the value at that index I. To fill the value at that index I, we may need to iterate through all the j's which are prior to the index I. So we iterate for all j's from I minus 1 to 0. Now, as per this recursive condition, only those j's are worth considering which are at least reachable. So we first check if dpj is not equal to minus 1. Then we also need to check this condition that the value at j should be greater than or equal to I minus j. Only then a direct jump from j to I is possible. So we have another condition if aj is greater than or equal to I minus j. Now at this point, we know the value of aj, we know the value of mj, which is minimum number of jumps required to reach index j. And now using these, we need to arrive at the value for index I. So if we were to use this index j to reach I, our minimum number of jumps to reach index I as a candidate answer will be equal to dpj plus 1. But then that may not be the final answer for index I, because for final answer we need to find out the minimum for all such j's, and to track the minimum we will then need another thing. We use the variable dpi to track the minimum. Now dpi will also denote the number of minimum jumps required to reach the index I, and we are using the same variable to track the minimum. Therefore, we initialize it with plus infinity, and with every j we get a candidate answer, and every time we get an answer we check if this answer is lesser than what is currently filled at dpi. If it is, then we update our dpi with this answer. In this way, as we iterate through all the j's, dpi will always have the minimum of all possible values. And finally, after coming out of these iterations, if dpi is still equal to plus infinity, that means there was no valid j that could lead to minimum number of jumps to reach I. That means I index is unreachable. So we fill dpi is equal to minus 1. And finally, we return the dpn minus 1, which is our final answer. So this completes our bottom-up approach for calculating the minimum number of jumps. Now what will be the time and space complexity of this approach? Time complexity will be big O of n square. Why? Because there are two nested loops. One loop to iterate over the whole array and fill value at every index. Then for every index, we again loop for all indices which lie prior to it. Therefore, time complexity is big O of n square. And what is the space complexity? Space complexity is big O of n because we are using one extra array here. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our target function. It takes array as an input and it has to return the minimum number of jumps that are required to reach the last index of this array. So first of all, we calculate the array's length and then we declare a new dp one-dimensional array of size n. We fill its first value with 0 because for first index to reach the first index we don't have to make any jump. Then we have to iterate. So we iterate from I is equal to 1 till I is equal to n minus 1. In every iteration our aim is to fill the value at dpi. Now to dpi, we initialize it with plus infinity because the value at dpi will be minimum of dpj plus 1 for all the j's that we can consider. So dpi will also track the minimum value. So we initialize it with plus infinity. Then we again iterate from j is equal to I minus 1 till 0 because now we have to consider for all j's, and using all these answers we will derive the answer for dpi. Now we have a condition that j should be reachable. So dpj should not be equal to minus 1. Then arrj should be greater than equal to I minus j so that there is a direct jump from j to I possible. If these two conditions are satisfied, therefore that means our index I is reachable via j. Therefore, candidate minimum jumps, that is the minimum number of jumps required to reach I, if we consider this j, a jump from this j will be equal to dpj plus 1. But that may not be equal to final answer dpi. Our final answer will be minimum of such answers across all j's. So we check if this is lesser than what we have currently in dpi. If it is, then we update our dpi. This way, once all the iterations are complete, dpi will have the minimum value. And in this way, once all the iterations of outer loop is complete, we will have the whole dp array filled. But we have to do one more thing. If dpi is still plus infinity after the iterations for all j, that means there was not a single j which could satisfy both of these conditions. And that means I is unreachable. So we update dpi with value minus 1. And in this way, we fill the whole array. And finally, our final answer can be returned from dpn minus 1 because this denotes the number of minimum jumps to reach this index. So this completes our code for bottom-up approach of the minimum jumps problem. So far, we have focused on figuring out the minimum number of jumps that it takes to reach the final index. But there could be an extension to the problem as well. We could be asked to not just return the minimum number of jumps, but also return the jump path. Or we could be asked what are the indices that were in the path to reach the last index with minimum number of jumps. How do we solve that? It is actually pretty simple. At every index I, whenever we fill the answer at any index I, that what does it take, whatever is the minimum number of jumps to reach this index I, we know what index j have we used because of these conditions and which j gives us the minimum value. So we know for this index I that what is the j index from which we have made a direct jump. So if we could store this information in some other array, that for every index I, which was the previous index j from which we made a jump, then figuring out the path would be simple. Since we have to figure out the path till the last index, we will know that what is the previous j from which we made the jump to reach here. Let's say it was this index, then we come here. At this point, we will know what is the previous j which we used to jump till this position. This value will provide us that. Let's say this was this index, and so on till we reach the first index. Therefore, using this new array, this another array, we can figure out the path. And this can be filled simply by figuring out that which was the j that we used to fill the value at I. So far, both of our solutions, the top-down DP solution and the bottom-up DP solution, have had the following time and space complexities. The time complexity has been big O of n square and the space complexity has been big O of n. Let us see if there is a further optimal solution possible. To find that, let us think about the problem again. Our aim is to reach at this index in minimum number of jumps. Now what do we know so far? Let's say we are starting from here. What are the minimum number of jumps to reach at this index? It is 0 because we are already at this index. Now we know, depending upon the value here, we know that there are some indices that we can reach in direct jump from here. For example, if the value here was 3, we could make a direct jump to either this position or this position or this position. In another way, we can say that all of these 3 indices are reachable by minimum number of jumps equal to what? Equal to 1. So, till this position, if the array was still here only, we didn't have to use any extra space. We didn't have to use big O of n square time complexity, and we could figure out the answers for all of these positions. This position can be reached in minimum number of jumps equal to 0, and these 3 positions can be reached in minimum number of jumps equal to 1. Let us now try to extend this beyond this position as we reach till the end. Now, these positions can be reached in minimum number of jumps equal to 1. But if we have to reach any position which is beyond this, then we will have to make at least one jump more. So now let us try to figure out which of these positions can be reached by 2 jumps. How will we figure out which of these positions can be reached by 2 jumps? Is it the value at this position? No, not necessarily. The value at this position could be just 1, and that means we could have reached till this position only. But the value at this position could be 9 or 10 or 8. That means we could have jumped to any of these positions by 2 jumps only. Therefore, we can say that every position has a maximum reach it can help us reach. For example, if the value at this position was 8, then we could jump till position 10. 0, 1, 2. 2 is the index here, and 8 positions further, that means index 10. And if this position had value 1, then we would be able to jump till only index 4, because 3 is the index here and only one position jump is possible. Therefore, if out of these 3 indices we could figure out whose reach is the maximum, then let's say we arrive at some particular index, let's say this, then all the elements till this index can be reached in 2 number of jumps. So we can see that depending on the values of all these 3 indices, we could have a maximum possible reachable index, and for all the indices prior to that, we will have the number of jumps is equal to 2. In this way, we can keep extending the solution till we reach the last index. So we can see that there is a semblance of building the solution. We can see that the solution is in sight. We can actually go through the solution using this approach. But we need to structure our thoughts better. So first of all, let us try to make a few observations. Our first observation is that every index has a max val it can jump to. Then we can see what we are doing. First of all, we are figuring out what are the indices where we can reach in 0 jumps. Then we are figuring out what are the indices where we can reach in 1 jumps. Then we are figuring out what are the indices we can reach in 2 jumps, and so on. That means, let's say if this was a new array called minimum jumps, we are trying to fill this array, and the value at this position will be our answer. Now, how are we trying to fill this array? To fill this array, we are iterating our original array. So let's say this was our original array, and in this array, we are filling the values of minimum number of jumps to reach at each of these indices. Now we can see that for a range of indices, these values are same. For example, from index 1 till index 3, all these indices can be reached in 1 jump. Then index 4 to index 7, all of these can be reached in 2 jumps. Therefore, what we are doing is we are identifying a range, and then we are filling all the values in that range with same value, same number of jumps. Now, how do we identify a range? To define a range, we can use 2 variables, range start index and range end index. Now let's see how will we figure out the values of this range start index and range end index. When we are at the first position, at that time these values are pretty simple. Let's say if its value is 3, then from 1 till index 3 we can reach by one jump. If its value was 4, range start would still be 1 and range end would be 4. If its value would have been 2, then range start would be this and range end would be 1. Range end would be this index. So this is definitely easy when we are starting from the first position. Now let's see what happens when our first range is done. When we reach at this index, how do we figure out what is our new range? So we know anything beyond this index will need one more jump. So index will start from this position. But what will be range end? Now range end will be the maximum possible reach that we can have from any of these positions. Therefore, there is a concept of maximum possible reach that we need to keep track of. Now, how will we calculate max reach? Max reach is simple. It is simply the maximum possible reachable index at any point in time. And we can keep calculating it as we move from left to right. As we move from left to right, for every index we can calculate what is the maximum index we can jump to. Now if that maximum index is greater than what we have in the max reach variable, we will update this max reach variable. Therefore, we will always have the maximum possible reachable index in this variable max reach. Therefore, when we reach here, we will have what is the maximum possible reach that we have in this range. So we can update the range end index, the new range end index, as per whatever is the max reach. So now we know how do we start filling this array. We know how do we update the ranges. Therefore, we can completely fill this array and finally return the answer from here. So just one complicated thing that we need to take care of is how do we update the range. We will update the range when we will reach the end index of the previous range, and that at that point in time the new range's start index will be I plus 1 and the end index for the new range will be the max reach that we have found so far. There could be a corner case as well. The corner case could be that this max reach is equal to the range index end index only. Therefore, it is not possible to jump further from this. In that case, we know that further this last index is not reachable. So we can directly return -1. So this is a solution whose time complexity is big O of n and space complexity is also big O of n. We are filling these values but without using two nested loops. We are filling it using in a single iteration. Therefore, time complexity is big O of n and space complexity is big O of n because of this new array. In fact, if we think about it, we don't even need this array. We know its values will be something like this 0, 1, 2 and so on. So we have the range start and range end index in some variable. Then we can also keep track of the jumps that we have to make in some other variable. And when can we find that we have one more jump to make? That will be whenever we have to update our new range. At that point in time, our jump would also be increased. So now we know how to figure out the indices which require 0 jumps, which require 1 jumps, which require 2 jumps and so on. We know how to update our ranges to figure out whose values are 1, whose values are 2 and so on. And we also know how to figure out what is the max reach that will be useful to update the ranges. So we have everything that we need to convert our thoughts into algorithm. So let's try to do that. Let us first try to understand the variables that we will have and what are their purposes. The first variable is the max reach. This will track what is the maximum possible reachable index till now. Then other variables are range start index and range end index. At any point in time, we will be dealing with a certain range. So we need to denote that range, and we denote that by using two indices. the start and the end. Then we need another variable jumps to keep track of what are the jumps that we have made so far. So now first let's see how will these variables be initialized. Let us say we make the first jump from our first index. Then our max reach is so far is equal to A0. The start of the range is index 1. The end of the range is max reach. And the number of jumps that we have made so far is equal to 1. Now we know that from index this till index this, we will have to make just one jump. And now we try to figure out what are the indices for which we will have to make two jumps. To figure that out, we need to keep track of what is the maximum reach possible. To figure out the maximum reach possible, we will have to go through every index and its value, because any index may lead to a new maximum. Now, that means we have to iterate. We have to keep on iterating. We have to keep on filling the values for a new range. We have to keep updating the range. But till when we will iterate? We will iterate till this end index is less than our last index. So we are iterating till our range end index is becoming greater than or equal to n minus 1. As this becomes greater than or equal to n minus 1, we know that the last index has been reached. Now what do we do in every iteration? In every iteration, we have a range and we start from start index and we move till end index. So we have another variable to iterate in the range. It starts from the range start index and it will iterate till it reaches the end index. And in every iteration, we have to first calculate what is the max reach. Now the max reach calculation is simple. It is simply the maximum of the existing value in max reach or I plus AI, because this denotes the maximum that we can reach from index I. There is nothing more that we have to do at any of these middle indices. What we have to do extra is at this range end index, where we will again have to update the range and we will also have to update jumps. When we reach the end index, we first check if the max reach is equal to the end index itself. If it is, then we cannot reach any further and therefore we return -1. If it is not and max reach is some index later, that means we have made another jump and we now have to update the range. The starting point of the range will be I plus 1 and the end point of the range will be the max reach. Then we will have to break from this loop, because now again there is a new range, so we will again start from range start till range end. And for every iteration of this, I will be incremented by 1 so that this loop can progress. Once we are done with the outer while loop as well, in the jumps variable, we will have the final answer for range end index, which will have crossed n-1. Therefore, we can return jumps directly. Now this is solving the problem in big O of n time complexity. It may seem like nested loops, but if we see carefully, every index is being traveled only once. Therefore, this is big O of n time complexity. And further, space complexity is constant because we are not using any other storage except a few variables. So this is our complete algorithm for the optimal solution for minimum number of jumps. There are a couple of very small edge cases where array size is really small that we have to handle here. We can see that directly in the code. Let us now go through the working code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function. It takes an array as an input and it is supposed to return the minimum number of jumps it takes to reach the end index of this array. So first of all, we figure out the length of this array. Then there are a few edge cases that we will come to later. First, let's see the implementation of the algorithm. So we have this max reach variable and it is initialized with ARR 0. We have the range start index and end index as variables. Range start index is equal to 1 and range end index is equal to max reach. Then we have another variable called jumps, whose value is 1 initially as we have made the first jump. Then we iterate. We iterate till range end index is lesser than n minus 1. As it crosses or becomes equal to n minus 1, that means we are now able to reach the last index using these jumps. And what do we do in every iteration? In every iteration, we will travel through whole of this range from start till end. We will figure out what is the maximum possible reach. Why are we figuring out what is the maximum possible reach? Because this will later become our new range's end index. So at every index we will figure out this what is maximum possible reach, which is simple but maximum of the existing value and I plus ARR I. And if we have reached the end index of this range, that means now we have to update the range. To update the range start index is I plus 1 and end index is max reach. And we also have made one more jump, so we increment the jumps variable. But there is an edge case. It is possible that max reach is equal to I. That is, max reach is equivalent to the end index. In that case, it is not possible to reach further in this array. Therefore, we can return minus 1. And this loop progresses by incrementing I. So, by this manner, as we have reached the end index equal to n minus 1 or greater than n minus 1, the jumps variable will hold the minimum number of jumps required to reach the last index. So this completes our code. But there are some edge cases that we should handle, which will not be handled by our algorithm. If the first element itself is 0, then we can't even make the first jump, therefore we have to return minus 1. And if there is only one element in the array, then we are already at the end of the array, then we have to return 0. So this will complete our code for the optimal solution. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.